In this video, we'll talk about radical expressions and Heron's formula. Operation of taking nth degree root is a reverse process to rising to a power of n. Here's the notation of nth degree radical. This is the radical sign. The expression under the radical sign is called radicand, and in the top left corner we indicate the index of the radical. This index sometimes is called order or degree. So this is nth degree root or nth degree radical of a. The whole thing is just called a radical. Notice that sometimes we use the word radical and some other times we use the word root. That really means the same. Radical is more general word. Root is usually reserved for the second degree root or cubic root. If the root is of higher degree, we tend to call it radical. Let's see the formal definition of nth degree radical of a quantity A. Well, this is such a quantity B that when we raise B to the n, we get back our radicand A. So in that sense, the nth degree root is a reverse process of rising to a power of n. The nth degree root of something is such a number that when we raise this number to n, we'll get the original something. Notice that if n is even, the above definition allows for dual answer. For example, if n is 2, that means if we take just square root of, for instance, 4, the answer according to this definition could be 2 or negative 2. That means that root 4, according to our definition, could be seen as 2 or negative 2, because both 2 square or negative 2 square will give us the radicand 4. So this is something that we are not very happy about. We don't want to have a dual answer. We want to define our radicals uniquely, which was the reason to agree to take just positive part of the root. And we call this positive part of the root the principal root. So even though the formal definition is as stated, we keep in mind that the answer for any even degree radical of something is positive. We choose this answer to be the correct one, and we don't consider the negative answer at all. This way, our definition of an even degree radical can be treated as a definition of a function, because we have a unique answer. So remember, the answer to the even degree radical is always positive. That's the principal root. From now on, if we refer to a root, we really mean principal root. Okay, let's state our rules again. Even degree radical of a positive number is defined as a positive number. However, even degree root of a negative number actually doesn't exist. D and E stands for doesn't exist. Why? Well, let's try. Root of negative 4. According to the definition, it's supposed to be such a number b that b to the 2, because the square root has index 2, so b to the 2 should give us back negative 4. But we know that any number squared gives us a positive answer, not negative, so there's no such b that will make this equation true, which means that the square root of a negative number doesn't exist. And the same justification can be done for any even degree root of a negative number. So please remember, even degree radical of a negative number doesn't exist, at least not in our real number system. What about odd degree radicals? We have some rules for those as well. Odd degree radical of a positive number is still positive. For example, cubic root of 8 is 2, because 2 cube gives us back our 8, so it complies with the definition. We can also calculate odd degree radicals of a negative number. Again, let's see an example. Odd degree radical, let's say cubic root of negative 8. Oh, that's equal negative 2, as negative 2 cube gives us back negative 8. So again, it complies with the definition. Odd degree radical of a negative number is negative. So you see, there is no problem with odd degree radicals. We end up with the same sign as the radicand. However, for the even degree radicals, they exist only for positive numbers and the answer is positive. They can't be taken of a negative number. We will be able to assign a value to this kind of roots, but not in real number system. That would actually be imaginary number, but we'll talk about imaginary numbers in the next course. Okay, let's practice simplifying radicals. Here we have fourth degree radical of 16. So we are thinking, what number when raised to the 4 gives us 16? Well, it's 2, as 2 to the 4 is equal to 16. So that's a justification that you can do in your mind. Next example, this is odd degree radical of a negative number, so the answer is still negative. And then we're thinking, what number when raised to the 5 gives us 32? Actually, it's 2 again, as negative 2 to the 5, it's equal negative 32. So notice that it's quite useful to know some powers of 2 and possibly powers of 3. Why don't we list the first 10 powers of 2? 2 to the 1 is just 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5, 32, 2 to the 6, 64, 2 to the 7, 128, 2 to the 8, 256, 2 to the 9, 512, and finally 2 to the 10, 1024. So this list of numbers would be nice to keep in mind. Those are very commonly used numbers. You can always count on your fingers, just doubling the previous power, right? And the more often you use those numbers, the easier it will be to recognize them. I would also suggest to memorize the first few powers of 3. It's a bit shorter list, but still quite often used numbers. 3 to the 1 is just 3, 3 to the 2 is 9, 3 to the 3, that's 27, and 3 to the 4, 81. Maybe one more, 3 to the 5, 243. So those are the most commonly used powers that it will be nice for you to recognize. Okay, let's continue with evaluation of our radicals. Cubic radical of 8 over 27. That's the same as cubic radical of 8 over cubic radical of 27. Since 8 is a perfect cube number, it's a cube of 2, then cubic radical of 8 is just 2. And 27 is a perfect cube number, it's a cube of 3. So cubic root of 27 is 3. And that's our answer, 2/3. Now, square root of a fraction. Again, we can split the square root to the numerator and denominator. So calculate square root of the numerator first. Here we have a pretty small decimal. But let's forget about this decimal and this 0. Let's look at the number 625. Do you recognize square of which number is that? Well, yes, it's 25 square. So for now, let's write 25. And let's think about how many decimal places should we take. Remember, this number, when squared, should give us 0.0625. And when we square a decimal, we actually take all the place values after decimal dot from both numbers. So, since we want to obtain 4 decimal places after squaring this number, the number itself should get 2 decimal places. So the decimal should be placed just before 25, 0.25. And you can check with your calculator. 0.25 times 0.25 is 0.0625. Okay, let's go to the denominator. Square root of 0.49. Square root of 49 is 7. Since we need to obtain 2 places after decimal dot, when squaring our number, the number should have 1 decimal dot, because 0.7 times 0.7 is 0.49. So that's good. Now we obtain a fraction with decimals. Since we don't like to mix regular fractions with decimals, let's change this fraction equivalently. We could, for example, multiply the top and the bottom by 100, meaning moving the decimal dot by 2 places, so we could obtain 25/70. And then we could reduce this fraction, for example, by dividing by 5. So the numerator becomes 5, and in the denominator, 70 divided by 5 is 14. So that would be our final simplified answer. Okay, let's carry on to the next question. 8th degree root of 5 to the 8. This is even degree root of a positive number, so the answer will be positive. What kind of number, when raised to the 8, gives us 5 to the 8? Well, it must be 5. So, let's observe what's going on. This looks like we can obtain the answer just by cancelling the index of the radical with the exponent of the radicand. Let's keep this in mind and see if this rule works in other examples. Here we have a 2011 radical of 5 to 2011. Again, what number when raised to 2011 gives us the radicand? Exactly 5. So yes, it confirms we can actually annihilate this index of the radical with the exponent of the radicand. But see the next example. Here we have 10th degree radical from -3 to the 10. Can we reduce 10 here and there as we did in example E? If we do that, we would obtain -3. Is that true? What do we have on the left-hand side? We have even degree radical of something, and this something is actually positive, right? Any number to the even exponent is positive. So even degree radical of a positive number should end up to be positive. Remember, principal root. So it's actually not -3. We need to convert this number to a positive one. So if we place the absolute value here, the final answer becomes positive, as it's supposed to be. How about 9th degree radical of -3 to the 9? Well, this is odd degree radical, so the answer has exactly the same sign as the sign of the radicand. But the radicand, -3 to the 9, since the exponent is odd, is negative. Negative, right? Therefore, the value of this odd degree radical is also negative. And this time, yes, we can just reduce the 9 with the 9, and we end up with -3. That's a correct answer. Here we don't use any absolute value. The only instance where we need to use absolute value is when we deal with even degree radicals. Why? Just because our agreement was that the value of any even degree radical must be positive. So we have to protect our answer by applying absolute value. So let's record this as a rule. If n is even, then the nth degree radical of x to the n gives us actually absolute value of x. So aside of just reducing this n and leaving with x, we need to remember to place absolute value. This is equal just to the x if x was positive or 0. However, if x by itself was negative, we need to change the sign. So leave the answer positive. So remember that root of x squared is not just x, it is absolute value of x. However, in case of odd degree radicals, we don't have such problem. We just reduce the n's, and nth degree radical from x to the n is simple x. No absolute value anymore. So that's something to remember. Anytime we deal with an even degree radical, we use absolute value in the final answer to make sure that we end up with a positive result. Unless we are told that all variables are positive, because if we know that x is positive, then we don't need to use absolute value anymore. Okay, let's try to apply this rule. Root of a squared. Well, since the root has invisible index 2, then we can basically cancel the root with the exponent 2, and the answer is a. However, we have no idea if a is positive or negative, so we need to place absolute value around it. Square root of x to the 6. Well, we could rewrite this as square root of x cubed and then squared, isn't it? Because when we have x cubed and to the 2, the rule is we multiply exponents. 2 times 3 is 6. So far, everything agree. And now we can basically think about reducing the index of the root with the exponent 2. So what's left is just x cubed. However, our root is of even degree, so the answer must be positive. We don't know the sign of this expression. It could be negative, right? So to protect our answer, we need to place absolute value around it. And now the rule is that we should keep absolute value as close as possible to the variable. So let's enter with this absolute value under the cube. That's the same as absolute value of x and then cubed. Okay, let's see another example. Fourth degree radical from negative x to the 4. Here we just simply can reduce the 4 and we end up with negative x. However, since that was even degree radical, we are obligated to place absolute value. Now, absolute value of a negative something, it's really the same as absolute value of just this something, because absolute value cuts off the sign anyway, right? So that will be the simplest form of the original expression. Let's go to the next example. Here we have cubic root of y cubed. Again, the two trays can be reduced, and we end up with y. Should we use absolute value or not? Well, no, because odd degree roots will carry the same sign as the sign of the radicand. So we are not changing anything here, just single y. Example E. We have a negative, let's copy it, and then the root by itself, it's an even degree root, so the answer must be positive. That will be absolute value of the input negative x. However, absolute value of negative x is the same as absolute value of just x. We do need to copy the original minus in front of the absolute value though, so that will be the final answer. And the last example, again, let's copy the first negative, and then we have odd degree radical from negative x to the 5. Notice that this negative x to the 5 is actually the same as negative x written in a bracket to the 5, because odd power of a negative is negative, right? Therefore, when we cancel the 5, we end up with just negative x with no absolute value because that was odd degree radical. Okay, so our final answer, since we deal with two negatives, it becomes positive, just single x. No absolute value. Overall, we really don't know if x by itself is positive or negative, but this expression simplifies to a single x. Now, we need to be able to use calculator to approximate certain roots or radicals. And in this example, we're asked to approximate to just 2 decimal places. So something like root 2 is usually not difficult to enter to your calculator, just because most of the calculators would have the square root sign available. So let's check it. On graphing calculator TI-83+, root 2 can be obtained by keying second x square, that's how we recall the yellow function root, and 2. Enter. So when rounded to 2 places, it's 1.41. This wavy equal sign tells us approximately. Now let's use your calculator and come up with the approximation of square root of 3. That equals 1.73. But what can we do when we wish to approximate cubic root of 10? Some of the calculators don't have the cubic root sign. As we see, there's no root 3 button here. However, under the math key, we have a list of roots and we can use third degree root as a fourth choice or nth degree root as a fifth choice. So let's see how much is third degree root of 10. We push number 4, which gives us third degree root, and then 10. We can either close the bracket or we can just say enter. That's approximately 2.15. If our calculator doesn't have the cubic root button, what we could do is to enter 10 and raise it to exponent by using such a birdie button. Then, in a bracket, write a number 1/3. Cubic root is the same as exponent 1/3, so we may write 1 divided by 3, close the bracket, and equal sign. Okay, that's the keying. Try it. You should obtain 2.15. So please check it out. Make sure that you know how to enter the radicals to your own calculator. Last one, fifth degree root of 100 can be calculated by introducing the fifth degree first, 5, then pushing the math button, choosing the fifth option. So in this keying, the 5 is taken as an index for the incoming radical, and underneath radical we have 100, then equals, and we end up with 2.51. The other way of obtaining this result would be to take 100 and raise it to the exponent, that's the exponential key. The exponent that we wish should be 1/5. Okay, this needs to be written in a bracket so the calculator knows that we raised to the result of this division, and enter. As you see, the result is exactly the same. You should obtain 2.51 when rounded to 2 places. Check it out. If you have any problem obtaining those values, check the manual of your calculator. In the next example, we are asked to estimate each root to the nearest whole number without a calculator. So how can we do it? Estimate, but to the nearest whole number. We don't need any decimals. Here, the useful thing would be to know your perfect square numbers. For example, 17 is positioned in between the two perfect squares, the perfect square number 16 and the next perfect square number, which is 25. 16 is 4 square, 25 is 5 square. Since 17 is closer to 16 than to 25, we can estimate this root 17 as 4, because 4 square is 16, and 17 is not much higher than that. So let's try this method to estimate root 70. What is the bottom closest perfect square number? Well, 64. What's the next perfect square number? Since 64 is 8 square, the next one is 9 square. 9 square is 81, and 70 is in between. Is it closer to 64 or closer to 81? Well, 70 is 6 units from 64, and it is 11 units from 81. That means it's closer to 64, which suggests the estimation of 8. Root 70 is approximately 8. You may want to use your calculator and check it. Okay, maybe the following example, try on your own. 115 is between which two perfect square numbers? Well, the bottom one is 100, which is 10 square, and the top one is 11 square, which is 121. Is our number closer to 121 or closer to 100? Well, this distance is 15 units, and that distance is just 6 units. So it looks like it's closer to that number. Therefore, I would estimate root of 115 to be approximately 11. And finally, 200. Well, 200 is in between 196, which is perfect square of 14, and 225, which is perfect square of 15. 200 is definitely closer to 196, so root 200 is approximately 14. Notice that to be fluent in this kind of rough estimation, it's really useful to know your perfect square numbers, at least up to 15 square. The next higher but very commonly used perfect square is 20 square, which gives us 400, or 25 square, which gives us 625. So those numbers, perfect square numbers up to 15, and then 20 square and 25 square, that's something that I would advise you to get familiar with. Here we have one more topic for this lesson, Heron's formula. Very useful formula when we want to find area of a triangle without knowing the height, knowing just its sides. So if we have a triangle, any triangle, and we have given 3 sides of this triangle, A, B, and C, we can still find the area of such triangle even though we don't know any of the heights or angles. Let's see how this can be done. First, let's introduce one more quantity called S. That will be defined as half of perimeter. half of A plus B plus C. It is called semi-perimeter. That's why S. So obviously we can calculate S as long as we have all three sides. Not a problem here. And then if we have A, B, C and the calculated S, we can obtain area of a triangle, how much space the triangle covers, according to this rule, taking square root of semi-perimeter and then semi-perimeter minus A, semi-perimeter minus B, and semi-perimeter minus C. Very useful formula. Let's keep this formula in mind to solve the following problem. Find the area of Bermuda Triangle to the nearest 1,000 square miles if the sides of this triangle measure approximately 850 miles, 925 miles, and 1,300 miles. Let's recall the formula for area. According to our formula, area of such triangle would be equal square root of, and now we need to start with semi-perimeter. So maybe on the side, let's calculate separately. What's our semi-perimeter? It is 1/2 of the sum of all three sides. So 850 plus 925 plus 1,300. Okay, we have 1/2 and this sum becomes 3,075. So when we divide by 2, we get 1,537.5. Okay, therefore we can build our area formula. It is semi-perimeter 1,537.5, and then we multiply this value by the difference between semi-perimeter and each side. So semi-perimeter 1,537.5 minus A, which is 850. Then again semi-perimeter minus B, which is 925. And semi-perimeter minus C, which is 1,300. It looks like a long calculation, but our calculators are patient, so it shouldn't be much problem to plug it in and figure out what's the overall value. Since there's so many large numbers to enter, to help yourself to do it a little bit more efficiently, you may want to store this number 1,537.5 and then subtract either this or that and record your half-step answers. I'm going to write those half-steps numbers so you can compare them and check if there's no mistakes. Make sure that you clearly distinguish between the dots that represent products and the dots that represent decimals. Okay, so we have 612.5 here times 237.5. And finally, let's multiply all these numbers and take square root. So it becomes 392,128.8 rounded to one decimal dot. This many square miles. That's really a large number. Approximately 392,129 square miles. That's the area of Bermuda Triangle.